Okay, welcome everybody to the Friday the 15th of May JKMRC Friday Seminar. My name is Nathan Fox from the Deviation Mining and Geology Research Centre at the University of Queensland. Also online and at the JK today is Professor Rick Valenza, who's the Director of the Deviation Mining and Geology Research Centre and currently the Acting Director of the JKMRC as well. Thank you online for joining us. Before we begin, on behalf of the SMI and the University of Queensland, based here in Brisbane, we would first like to acknowledge the traditional owners of the lands on which we meet today, and we pay our respects to their ancestors and their descendants. Today it's a pleasure to introduce today's speaker, John Jackson from Imdex Mining and Technology. Many of you, of course, will know John. He's got more than 30 years of varied experience in the mining industry across a range of commodities and roles. At Imdex currently, he is focused on innovation and technology development, which includes the integration of technology, workflows, and people to improve productivity and value in mining operations. Of course, before this, John held roles at JK Teck as a principal consultant in geometallurgy and commercialization. He's also been working in exploration and feasibility study manager in Australia for Inco and Vale, covering copper, nickel, uranium, iron ore, phosphate projects from greenfields to advanced stages. Prior to this, John was also the Manager of Resources and Technical Services and the Principal Geophysicist at the Sons of Gwalia in WA. And he's also held roles at the, in geophysics and geology, including 10 years at MIM Exploration and also the Tasmanian Mines Department. John is a graduate from the University of Tasmania, holds a BSc Honours degree in Geology and Geophysics, and also a Master in Business Technology from the University of New South Wales. So today, John's going to discuss how to achieve productivity improvements through the application of technology, automation, and data analytics. And his title of the talk today is Enabling Short Interval Control Using Spatial Dense Geoscience Information Beyond Grade Control. Before I hand over to you, John, I'd just like to say to everybody online, we have a question and answer session that's managed through the Q&A tab in the Zoom link. If you could ask questions in there, and myself and Rick will do our best to moderate those to John at the end of the talk. So without further ado, John, over to you. Thank you.
So thanks, Nathan, for the introduction. For this talk is split into three parts. A brief introduction onto the motivation of why we've gone down this route. The second part is looking at some of the technology, a very high level overview, and also looking at a few of the outcomes to date. And then the third part is around looking back on our innovation journey. How we got to where we are, what started it, who was involved, how it all came together. Because it has been quite a winding, torturous road over a number of years. It's not straightforward. So short interval control, also known as short-term planning in some cases, or just short-term operations. But it aims to adjust operations in real time based on actual conditions to meet shift goals and short-term planning targets. So it's about adapting to what's in front of the operation in real time. Now the focus of SIC commonly, and not unsurprisingly, is on improving overall equipment effectiveness, because that's the easiest place to start. Scheduling, equipment uptime, usability, availability. But here we're looking at it from a rock processing perspective, and it's about making the decisions to balance cost benefits, to maximise the value, and value being a broad value term, not just costs or value in terms of metal production or ore production, but also waste. Predominantly waste beneficiation, what goes to the plant, what doesn't go to the plant. And the whole objective is to get the most appropriate decisions with the material that's in front of you that's best for the operation, given the constraints that are often in operations that change on a day-to-day, week-to-week basis. The initial focus is going to be on blasting for the very good reason that it's the last in situ opportunity for knowledge and option analysis. So it's when and around blast holes before we blow it up. So it's when it's in situ, we can make our best decisions then on what happens, where material goes, allocation, what treatment route, and then also what strategy should be done for the processing for different material types. So it's more than just grade. There's a lot of levers that operations can pull along with constraints, and this is just a few of them listed out. So you've got blasting from a fragmentation perspective, there's big parameters, and a lot of these are interdependent. They're not live in their own little silos. So for instance, some of the digging issues on direction depends on the ore body, depends how you blast it. There's beneficiation, there's waste allocation. There's a number of operations that their schedule, their short-term schedule is driven by waste. What material they have, where that should go more than the ore itself. Stockpiling. And then in the processing side, comminution, precondition, what's the crushing process stream, blend by size, for instance. What's the operating strategy for material type coming in? Should you change it on a day-to-day, hour-by-hour or week-by-week time frame? And more problematic is recovery, but the same concepts flow through to recovery as well. So if the goal of SIC is to adjust operations in real time based on actual conditions, then as I sort of noted before, that blast holes provide the highest spatial resolution in order to make some of these short-term decisions. In a perfect world, this knowledge would just be a higher resolution view of that obtained from grade control, if the operation does grade control, and before that, resource definition. So you have the same common model, you're just improving resolution. Some calculations around blast hole sampling. Often the sample, there's one sample per blast hole. That's fine, it's very 2D. When we go into a 3D world, we're increasing the knowledge and the data by roughly around 100 times, depending on exactly the operation and how it's working in the commodity. And we live and work in a 3D world really until it hits that conveyor belt. Then it sort of moves into a 1D. So if we can get the high resolution rock knowledge, we can undertake what's commonly called precision mining. And there's a lot of analogies in other industries, and probably one of my favourites is agriculture. There's precision agriculture. It has similar issues to mining. They have variability, weather, crops, yields, and they're trying to maximise their value from that crop, particularly broadacre cropping, given the conditions they have at the time, the weather, the soil conditions. Viticulture is quite similar as well. And in some cases, they've gone further down the precision route where the customer pulls and it flows back through to the chain, and they look at their blends and their harvest times in order to make what the end customer wants. So we have usually quite a blurry view of the world. So to enable precision mining and SIC, we have to improve that current blurry view and get a clearer perspective. In some cases, we actually have no view of downstream properties, and that can lead to surprises, some good surprises, and often some not so good surprises. So we want to try and move from the blurry view to a very clear view. So the question here is, if you had to operate at maximum speed, you had to run through this field, which perspective would you prefer? The one on the right or the one on the left? I think I prefer the crisp one as I'm running through that field. At least you know what's coming up and you can make decisions about what to avoid, what not to avoid, what's going to happen. So to get that clearer perspective, if we take some analogies or a couple of examples, for grade, for metal content, we don't do grade based on geological units anymore. So we don't have an average grade for a geological unit. We take our exploration and development data and we build block models and look at the heterogeneity that we see and that guides development. We then go further and we go into grade control, either from blast holes or from grade control drilling, and we get a higher definition of what the mineralisation, what the metal content and spatial distribution is. Just those two slides are of the same RL, of the same mine, of the metal content from the resource block model versus the grade control drilling. So you can see a significant difference in the spatial resolution. If we take something like blastability, for instance, we commonly take an average blastability factor on a geological unit. In some cases, but they tend to be the exception, blastability models are built off the exploration and development data as a guide to the operations guys on what they're likely to expect and how they could start adapting. Very different view of the world compared to the left-hand side. And from a grade control point of view, we don't know what blastability looks like at high definition, high resolution, and then what levers we can pull. So this is where we're focusing on this area of material characterisation in the grade control, be it from blast holes or true grade control drilling. But primarily right at the moment, it's focused on blast holes. So what technologies do we actually have or commonly used for blast hole sampling? Well, we drill the hole to start with, and MWD has been around for quite a while. So we have, at the basic level, there's rate of penetration, and then up into some of the specific energy calculations that come off the rigs. And then in the advanced area is detection of discontinuities, fractures, things like that. But MWD's been around quite a while and it does suffer from a number of issues. Geology-wise, we tend to be 2D. We tend to be taking samples of the blast cones and then either assaying it, visual logging it, or using instruments like the HALO NIR system, hyperspectral scanning. There's quite a few multi-element XRF, quite a few systems for that. It is rare to take downhole samples from blast holes. Systems do exist, but there's a lot of issues with sampling, on knowing exactly where the samples come from. Wireline logging has been also around for quite a while. Less common in metalliferous, more common in coal operations, and caliper, density, gamma are quite often undertaken in coal to a limited degree. And then more recently, some downhole geochemistry, elemental techniques have come along, like Sedern's fast ray system. Now, one of the problems with the geology side, where it has its limitations, is from that 2D view that we are taking point samples, average across from the whole hole, and there's always the arguments that go on around sampling issues with blast holes. Where we're focusing on is wireline logging and logging of blast holes from many perspectives, and that's where we'll focus going forward in this presentation. So it's not new. I'll be very clear about that. Well, probably one of the best examples was from the late 1990s, early 2000s at Century Mine, where they were geophysically logging blast holes. They were integrating MWD data plus the logging data to better define rock mass. And the guys up there, of which there's a number who are known from Brisbane and attached to UQ, did some very, very good work, and they showed some great improvements. They improved the short-term geological model. They had a reduction in dilution. They had better control on the mining schedule, and from a safety perspective, they reduced the spotters on the bench. So it showed value, quite a bit of value, and the question was, well, why wasn't it adopted more widely? This is still held up as the type case of geophysical logging in metalliferous operations. So some of the challenges was the speed of logging. You'll notice here that they logged every second hole on every second row if there was time. And time was not just the logging speed, it was also access to the bench and some of the other constraints and the number of people on the bench. There was the speed of data transfer and analytics. So when this was happening was right when GPS, RTK GPS was coming in on equipment. It was pre-high-speed connectivity on mine sites. There was a lot of manual handling of data. So the turnaround times didn't necessarily match the operational speed. There was also adapting exploration tools. So there was limited sensor stack or having to use multiple tools. That slowed things down. The tools were often skinny because they were from exploration. So there were a few challenges. This was quite a while ago. So what we've sort of taken is to modernise that concept, bring it into the current times. So we've created a fit-for-purpose sensor, multi-parameter sensor for blast holes. So it's reasonably big, chunky, because we are dealing with large holes. We do have the ability to have a fat sensor, fat probe, but we are constrained by trying to keep it as short as possible. So the version 1 of the tool has natural gamma, caliper, hole deviation, conductivity, magnetic susceptibility, and then water level detection and external temperature, so hole temperature. So that's one part of it. The other part is the deployment system, and what it is at the moment is a small cat excavator that has been, a new word, roboticized. And that was done deliberately because a cat machine on an operation is normal. There's cat machines running around all over an operation. So they see another one. The adoption is really quite easy. It's also, serviceability is very high. The mine can service it. It's not a bespoke high-tech bit of equipment that is hard to service. There's existing service channels. Either the mine site or the local community can usually service these little cat machines. It's also some safety considerations that it is being automated, roboticized, so it's removing people from the bench. And it's so sort of identifiable from a cat thing with the yellow cat machine and the way it looks, that when we took it to South America, it's been nicknamed the Wally. So across the radios, there was always talking about the Wally. Where's Wally? Out of the, this is the Disney film, I think, Disney series. So that's what we've developed, and it's just a couple of snaps, happy snaps of the what we call the BLASTDOG system, and the 1AS being the machine itself. Out on bench, one in a metalliferous operation, and then one in a coal operation. And we've been on site a few times now, trundling around, logging quite a number of holes. So we'll have a look at some of the data that's come out of the system by looking at some assumptions of how people treat the parameters now versus what the actual conditions are. And this is referring back to the SIC, which is about adapting the operations to actual conditions. So if we start with the profile or gauge of a blast hole, which is what the blasting engineers use as an input into their decision making, the assumption is holes are perfect cylinders at a nominal diameter. So here's a downhole view of some blast holes. They don't look particularly cylindrical, and they're definitely not at nominal diameter. And that's backed up in this particular example, diameter from our caliper data for a through seam coal hole. And you can see the nominal diameter for this hole was 250 millimeters. You can see that generally it's sitting above it, and there's quite a lot of variation down that hole. If we go to the metalliferous operation, these are 3 holes in a row. They're only 4.5–5 meters apart, adjacent holes. This is the cross-sectional volume or cross-sectional area for an interval relative to its nominal size. So you'll see there that anything in the yellows, oranges, reds and purples is above 30% nominal hole volume. So if you have a look in particularly this hole here, there's a large number of meters in that hole that is plus 30%. So that means that you will be loading more than 30% more explosive in that hole to reach a certain level than what you were expected. So that means that the energy going into that particular hole is significantly higher than you expected. Same, this one here is not quite as bad as this one. It has less zones. And then this hole here is pretty good. It's very close to normal. So there's quite a lot of variability over a very short time in these hole volumes. If we have a look at deviation, from hole deviation from below, and this is important from both a blasting perspective, for where energy distribution is going, but also from a geology short-term modelling perspective. Where are the holes? Where are the contacts actually? So the assumption is the holes don't deviate. They are according to plan. This is an example from one site where these are angle holes and it's an oblique downhole view, plan view of the holes. So if the holes are straight, they should be dots, similar to like this hole G38 and D39, G36. They're pretty straight. We're looking straight down the hole, so we see a dot. You can see over here, D34 and some of these A holes deviate quite significantly. The A holes are the back row, so they're the ones that come back in and around, back into the wall. So the energy distribution in these holes is going to be very different to what is assumed, and also the contacts, in this particular case where top and bottom of coal are also shifting in space. So the short-term model is going to be very different between what they think, if we assume no deviation, compared to what it actually is. Also relating blasting and geology is structures and fractures. Often in blasting, as went back to the common view of blastability, that we were using it on a geological unit basis and it's homogeneous. We take an average value. So the rock mass is considered generally consistent. Structures provided is fact. So the operations guys will get, here's a structure running through here, provided by the geologist. That's often based on the resource development drilling, which is wide space, so there is uncertainty in that is hard to portray across the operations, but because it's aligned on a map, it's taken as fact. And people design to that. So some actual conditions. This is some logging of 2 holes on the same blast pattern. You'll see here in this one, these are reasonably short. That's about 10 metres. There's reasonably high fracture frequency with the occasional large open fracture. As compared to this guy over here down in this zone, where it's very low fracture frequency. It's quite smooth. There's no large fractures being opened up. And you can see in real life, there's this, in this particular picture, there's this big competent block sitting in here, surrounded by a sea of quite fractured material. Strangely enough, when you put the same energy from the blasting point of view into both of these, you get very different outcomes. This guy produces oversize, this one obviously is quite fine. So the question is, should you change the blast, put less energy into this and more energy into that one? Actual conditions change the operational parameters. And down here, there's obviously been some large competent material that's been blasted and significant oversize. So we're starting to see that on quite high variability on quite a short spacing. And we're starting to be able to map out fractures that go through the pattern. So just basically interpolating from across holes. Another one is on geology material types. So because we're trying to get consistent quantification of geology and assays from blast holes can be problematic. Geological logging appears to be reducing rather than increasing, I think is a fair trend. It's simplified into 2D domains. So in this particular case, this is an example of lithology just on a blast hole basis. Here's some material classification on a blast pattern. This is just along a road to make it easy to see. These are 10-metre holes, so they're quite short, and there's a lot of variability in here. It ends up, it turns out that this yellow red zone in here is alteration, and that's where the mineralisation tends to sit. So if you knew where this zone was within your bench and you just didn't have, grade goes from here to here in the surface as points, would you blast differently? Would you dig differently? Would you load the holes differently? The short answer is yes. Another example is, again, this is looking at alteration. This is starting to see quite a lot of complex geometry inside the bench. Again, these are only 13-metre holes, 12-metre holes. So we're seeing quite a lot of character and short-range variability within these holes. And this is a coal example where we're looking at the coal seam with a parting in the middle, and then differences in material characteristics above and below the seam. It's a bit hard to see, but there's a small zone in here which is quite different. That is a little hard cap of about 1 metre or so that sits on top of the coal, of which the equipment doesn't like. dig rates are down and equipment damage is up. And you can see that that isn't everywhere. It does change across the blast pattern throughout the bench. And the interburden to the next coal seam is also changing along strike and throughout the bench. So there is, in some cases, quite a bit of variability within these, even within a coal blast. So that's an example of the outputs. This is our sort of deployment roadmap, and where we're aiming to get to is an off-bench fully autonomous system. So it's supervised back in like a Rio Centre back in town or maybe on site, and it's following the rig around, logging the hole, providing the data through. It can be operated anywhere from remote manual up to eventually fully autonomous. At the moment, we're sort of around the line of sight step autonomy mode. So we still closely supervise it, and it does a number of its functions autonomously. And depressingly, it's a lot quicker than us logging manually. It's a lot more consistent, and it doesn't mind the heat as much as we do. So when it's up and running fully, it is a lot more autonomous. So that's an example of just the technology. We'll now move into having a look at how did this project come about and how our part of the technology fits in with other parts. So it's a bit of a look at the innovation journey. So the development of the BLASTDOG is part of the instrumenting the bench team within CRCORE, and the project is material characterization at the time of last hole drilling. It's shortened to ITB for obvious reasons. And it's a MetsIgnited collaborative project with AngloAmerican, Orica and Teck. So we've got resource companies and Orica is the blasting company involved as well. So it was born from a dinner conversation at a CRCORE implementation council meeting, where there was a bit of mixing and talking of minds around some of the problems in the industry. And there was a realisation that not one company or organisation could provide the entire solution. And that led to discussions between organisations with similar visions. And hence the coalition of the willing, which obviously became the cows. Now this morphed over had quite a gestation period. There were a number of companies who individuals were keen but couldn't get the organisations themselves to come on board. So it ended up with those main four companies. There was a lot of discussion with other resource companies besides Anglo and Teck, and that led to the driver for the short-term blast hole logging. Because it had direct impact, you could see the value fairly easily. It was measurable, and then it could be taken back upstream into the grade control, then resource development, and back into exploration. So the overall objective for the project was to acquire, integrate, and transform data from blast holes to optimise drill and blast outcomes for downstream processes. So we really narrowed it down to just focus on the connection between, around how you blast, the connection between the rock and the blasting, but taking into account downstream processes. So at the end of the project, we ambitiously wanted an autonomously deployed system for logging, automated spatial domaining of inferred physical properties and fracturing, spatial domaining of that, be it block models or as volumes that automatically fed into blasting systems, and creating complex blast profiles and drill designs to achieve optimized outcomes. So it's pretty ambitious. And we're taking a systems perspective of this. It's not just each little bit in isolation. So we do have NWD data and in some cases LWD data. We are logging ourselves, and then that data is being fed up into the cloud. We're running through a bunch of analytics to convert the data into information and rock knowledge. That goes into a spatial visualization of it, be it a block model or a volume. It goes across into the blasting world, who then do optimized blasting, and then there's the feedback loop of looking at the post-blast metrics, which includes fragmentation, distribution, instantaneous dig rates, whatever data we can get our hands on at the back end to help inform the analytics. So it's a systems view. So some of the resource companies' perspectives, it was to take advantage of the vast amount of D&B holes to provide relevant information for operational control. So even in coal, where logging is part of doing a geologist's job and part of operations, they log around 2 to 5% of their blast holes, often less than 2, because operational constraints come into play. At one of the sites we're working at, they do 70,000 blast holes a year. So that's a lot of holes. So the idea is to increase that percentage to help characterise, from a coal perspective, coal and the waste material. It's also to develop automated processes to allow picking in coal case, top and bottom of coal, and characterising waste material automatically. So it doesn't require a geologist or someone else to sit down and interpret the logs and do all the analytics, because it won't happen. The guys on site do not have time to do that sort of work anymore. Once the material characterisation of D&B holes will start learning, that's an enabler for smarter, cleaner mining down the track. So you can start linking technology that's being pulled through the system with the actual rock properties. What are the opportunities? How do we value them? How could we use it? And there's a plethora of these, from bulk sorting to digging systems to beneficiation, screening, grade engineering. There's quite a few. And then it's also to develop relevant material characteristics for input into downstream processing decisions. So like I said earlier, things like it might be mill hardness, for instance, rather than just an average or interpolated block model, or data that's being interpolated in the block model from quite wide, sparse point data. We're getting some high resolution data, as long as we can connect the properties that we're measuring to those hardness values. And also there's improved management environmental conditions with blasting, particularly around dust and fume generation, vibrations, some of those aspects that affect the social license to operate. So like any good plan, we had a plan, we went to site, and the plan needed significant adaptation. So one of the challenges that the first site we went to was a coal site. Originally, we were envisaging working on metalliferous sites, but one of the companies chose a coal site, and we went to site, and we were confronted with these large blast cones. The D&B supervisor asked what our plan was. Oh, we were going to come in with normal truck mounted system. We were going to log all the holes manually to provide the data to build a value proposition to go down a more autonomous route. The D&B supervisor said, so you're telling me you want to log every hole? Yes. And I should add, the D&B supervisor had worked at Century during the logging of the blast holes in that late 90s, early 2000s period. So he knew what we were up to. And he said, not in quite these polite words, but not on this site. Go away. And the reason was that the amount of time required to prepare the holes and the cost is significant, because from an HS&E perspective, it's problematic to hold a big probe and manual handle it and try to get it over the cones. Their procedure is to clear the cones. To clear the cones, you have to put a gas bag in every hole, then get the loaders out, clean it, and then when you're doing, 800 hole shot, where's all that material going to go? You're creating dust. Then you have to go and find the hole afterwards, and then pop the gas bag and pull it up, and it's impractical. So that very quickly pushed us towards a different deployment system. So this is where additional collaboration came in with a Brisbane startup, Universal Field Robots, which we had been talking to over the previous 6 months about another project. And we went to UFR and sat down with Jeff and the guys and said, we have a problem. We think you may have a solution. What do you think and what's the timing? So this was January 2019. By February, it was mid-late January, early February, we had a concept of how we were going to do this, how it could be done. And then in June, so 4 or 5 months later, it was on site working in a robotic fashion. So it was a very, very quick scale up and deployment. And this is just another picture of it, more recently logging over a significantly large blast cone. So this was a bit of a change for us. We were originally going to have the autonomous towards the back end of the project. It's come way forward, and that whole path has been accelerated. It took a lot of work, a lot of collaboration between ourselves, UFR, and the companies, because getting one of these things on site, it's novel, it's unique. There is no training modules available, certifications. It's bespoke, it's brand new. There's a lot of HS&E hurdles to jump in inspections. There's a lot of computing in there. There's the electrical standards. There's a whole lot of stuff in there. From an Orica point of view, it's starting to head towards their data-driven blast optimisation, where they have what they call dynamic geomodelling, which is basically properties relating to blasting at the actual conditions, where they can start taking that information and tailoring each individual hole on what product they load, how they load it, and the optimal sequence of detonation to be able to create optimal outcomes, while limiting those like wall damage, fumes, air blast, and all these vibration at the same time, rather than just loading every hole assuming it's the same. as we've started collecting data, that's being fed to Orica, and they're working on how they would actually do this in real life. So one of the objectives, and we've sort of been delayed by coronavirus somewhat due to lack of site access, but the objectives when we can get back on site is to be able to log the hole, interpret the data, feed it through to Orica, change the loading plan, execute the new loading plan, and fire the bench and look at the outcomes. And then try to assess against what they would normally do versus the modifications. We're also extending the system from beyond blasting, where we'll integrate the data into a whole series of models, and then that will run through IES. And to run a whole series of scenarios and options around blasting and comminution primarily, and potentially location. And we'll look at the actual outcomes from some of these blasts together with what the hypothetical scenario and option outcomes are, to look at values from a throughput cost versus benefit perspective, to start modelling some of those and then start implementing those on site. So we're heading towards the light on the hill. This is from CRCORE that gives sort of a size of the potential prize, and the benefits are quite large. If we can pull some of these off, we'll make significant gains in improvements, not just from a cost perspective, but also from the broader value perspective of better managing waste and environmental things like fumes and dust and some of those aspects. So the journey continues, and it's going to be twisty. It has been to date. We change, we have to be quite adaptive. We pivot quite a lot as we get more information, we interact with the sites, we understand more of the workflows. We also, because everyone's also doing work, like Orica is learning how they can use this data, how to model, what to change, that feeds back into us and how we operate and what we need to do. So we will get there. When we can get back on site is anybody's guess, but hopefully it's in the not too distant future. We're thinking maybe a few years at the moment, particularly for international. And we'll keep going down our winding and twisty road. And on that, I'll conclude with some acknowledgements. So this is a team effort. It's quite a significant team. So from Imdex, I need to acknowledge Dave Lowy, who basically drove this over a number of years, herded a lot of cats over the time, and then obviously our development team, UFR, Jeff Sterling and the team here, AngloAmerican, particularly Paul, Max and the site guys, have been incredibly helpful and supportive. Orica, and Steve Boyce was one of the drivers who's recently retired. Teck, Chad and Mark, CRCORE and MetsIgnited. And it's quite interesting that a lot of the drive for this is actually coming from the geoscience groups, supported by the operations drill and blast, rather than being driven from D&B, supported by geology. And I'm not 100% sure why, but I think it's a combination of bandwidth. Some of these guys are corporate, so they have a longer term vision. They're not caught up in the day to day, so they can see where it could head and can sort of lead it through the system. So on that note, I'd like to thank everyone for their attention, and I'll take any questions, I guess.
Now for the first time in 8 weeks.
It's a bit different having a live audience plus the webcam
Plus
and the screen. Not sure exactly where to look at times.
Thanks very much, John. That's a really interesting talk. You could see a great success story from conception to application, so thank you. We haven't got any questions yet online. Anybody listening, if you do have any questions, please ask them to John. In the meantime, Rick, I don't know if you want to have a scout around the room, if there's anybody in the room that actually wants to ask any live questions again. First time.
I've got a couple actually, but I'll start with the question is around, and this might be an easy one to answer, but how you did it, I'm sure wasn't easy. The BLASTDOG robot, or the BLASTDOG machine, is that fully autonomous or is it controlled?
It's very close to being, it's fully autonomous in constrained conditions at the moment. Take it out into the wild and it requires a little too much intervention right now, but that's what's being worked on. We're going through what we call stepped autonomy, where we're just basically, we're sitting there controlling it, but it's about pushing a few buttons in sequence as we learn where it trips up. So it can travel between holes, it can automatically align the arm to the hole, and it does auto winch.
And then around the sort of taking the actual blast hole data and turning it into a model that, I mean, I know you talked about that a little bit, but how, is there scope for improvement in that workflow? Is
yes. We're just at the start of that journey.
This is a loaded question.
Yes,
I'll talk to you about it later.
Yeah, no, we're very much in the early stages of that. We have a platform, so the data gets transferred directly from the machine up to the cloud in real time, or near real time at the end of every hole, either via 4G or satellite, depending on the comms system. And then the analytics engine takes over. It does the processing, so there's a bit of QA cleansing stuff happens at the moment, then some of the analytics, and then there's a series of outputs for varying customers, some from the operational side, from D&B, like the whole profile, the volumes, the collar lengths, the collar diameters, hole depths, where the water is, temperature to identify hot holes for reactive ground. So there's a whole series of outputs there, and then there's more we'll call it the blastability geoscience side, which goes into surfaces and block models. Now, some of that's not as automated as we would like, but it's a work in progress.
Yeah, on that point, John, I was interested to hear you say that you thought it was more the sort of the geologists who were driving it than the drill and blast engineers. And I can see why, because you were talking about improved throughput with better fragmentation from the blasting, but then there's all those geometallurgical aspects as well.
Yeah, and I should add, particularly with Teck, because it's a metalliferous mine, the mets are heavily involved as well. It's not just the geos. It's really looking at it across the system, the line to mill type perspective. Yeah, but trying to get everyone aligned, it's hard.
I see we've got some questions online now, so I don't know if Nathan, you want to go to those.
I suppose in a follow-up way, Ibrahim Salimi is asking, we're firstly saying thank you for the presentations, obviously very good, but there's a question about the fracture frequency being directionally dependent. So I guess there's almost a geological kind of question. Is it sufficient to incorporate the rock structures in blast design, or do we need to be more comprehensive in terms of modelling, so maybe using discrete fracture network modelling?
Yeah, that's a good question, and I don't have an answer for that. It comes down to a time issue, I think, because what's happened is because this data hasn't been available, the work into really advancing the D&B models from an operational perspective where they can be run quickly, hasn't really been worked on because the data isn't there. Also, on the other side, no one's really advanced the logging side because there's nowhere for the data to go. So it's sort of been like catch-22 or Mexican standoff. So I'm not sure I'm answering the question exactly, Abraham, but it's really, those two need to talk more and need to marry more and come up together. I don't think we're at the stage right at this moment in time where the fractures can be taken into account in a timely manner for, say, discovery.
Are we at a point where people can still get into pits and map the faces? Is that going to be useful?
Yes, but that's, again, it's 2D. So there's a lot of interpretation that needs to take from those face mapping into a 3D blast pattern.
Okay. Just a question regarding whether this technology can be modified, so potentially in underground operations as well.
Short answer is yes, and we're looking at that as well.
Okay, excellent. Constanza Paredes is asking, can you import the drill hole coordinates as drilled from the high precision GPS in the drills through the fleet management system into the robots to have automatic positioning of the robot?
Yes, that's actually one of the requirements for full autonomy. It's that we need the data coming from the drills in order to position the machine, know where the machine has to travel and how to position itself.
Excellent, that's very advanced. So probably our final question has come online from Dion Weatherly at the SMI. Again, congratulating on your great presentation. But the question is how to quantitatively assess the benefits of this post-blast. So once everything has been obviously smashed up and thrown on the floor, how much of the high resolution bench scale data can be carried forward to downstream processing through haulage, stockpiling and conveying?
So it's a good question, Dion. The blast movement models have been improving over time. So again, that's another change. It's not just the technology that I went through. There's a whole lot of peripheral technology that's been improving as enablers that part of the system, and blast movement modeling is one of them. I think you can do a pretty good job these days with some work to model where material goes within the muck pile from a number of different ways. I always have had an issue with stockpiles. Once you hit the stockpiles, then what? How important it is, I'm not 100% sure, and I know there's been lots of discussion over the years inside this building about stockpiles. But yeah, that's where some of it can break down, and material tracking through the stockpile, or even modelling material flow through the stockpile, is a question I don't have an answer for.
That's perfectly fine. Thank you for that. I suppose just maybe in following up for that, our speaker next week, might be a good time to plug this, is David LaRosa. He's the Executive Vice President from Ore Control Blasting Consultants, and he's actually going to be talking about grade control in the time of coronavirus. So that's next week, Friday the 22nd of May, for those that want to kind of continue this discussion and see where that technology is going as well. Hopefully that kind of addresses some of those questions there from blast space. It'll be interesting.
Yes, I'm sure Dave will, because that's a sort of another component, is the ore control side. It's critical. Whatever ore happens to be, I won't get on that hobby horse.
Okay. Well, I mean, if that's all the questions, Rick, if there's no more questions within the room,
Nope.
Just like to thank John one more time. Thanks again. And we look forward to seeing you next week as well. Okay. Thanks, everyone.